classes we will be solving few more problems in different dimension of complexity from the different reactor systems. Let's see this case. This is a specific case where we are talking about a Plugflow reactor, and one specific enzyme is there which acts as catalyst in the fermentation of reactant A. At a given enzyme concentration in the aqueous feed stream volumetric flow rate is given already 25 liter per minute. Find the volume of Plugflow reactor needed for 95% conversion of reactant A. The concentration of the reactant A is 2 mole per liter, and the kinetics of fermentation at this enzyme concentration is given by one enzymatic reaction where minus Ra equal to 0.1 Ca divided by 1 plus 0.5 Ca. So it is typical enzymatic reaction, we know. So before we are going to solve, we already know what will be the performance equation for Plugflow reactor. We will be always using the same equation, so nothing to tell here. So for Plugflow we know tau equal to Ca0 is x0 to xa dxa by minus Ra. By the way, here minus Ra is the rate expression which you already know, but this equation is already in terms of Ca. I have to change, or we have to change in terms of xa because the integration is in xa. So that is one of the big activity here. So we can write Ra equal to 0.1 Ca 1 plus 0.5 Ca. So Ca means Ca0 into 1 minus Xa. So this change we are doing, and as we know Ca0 value is 2 mole per liter, we are putting it back. So the expression for Ra is becoming in terms of Xa. Now if it is becoming in terms of Xa, we can do the integration also. Now tau is unknown, and if we are putting it Ca0 values, for example 2 mole per liter, we are plugging it here Ca0, and Ra component in terms of Xa values whatever we derived, now we are plugging it back here and we are doing integration. So this integration we can do it essentially, it is a we know the boundary of the integration 0 to Xa, and Xa is actually you are asking for 95% conversion. That means so 0 to 0.95 and this integration. So this integration actually I am leaving it to you. You can do the integration part. Again you can do it by parts. So we can write 2 by 1 minus Xa minus Xa by 1 minus Xa. So two components we can do the separate integration, and it is possible and easy also. Once you put those values, we are getting it is around tau is coming around 39.45. so tau equal to, you already know, it is actually V by U. V is the volume of reactor, U is the flow rate, you should always keep in mind. So this value is 39.45, and flow rate is given 25 liter per minute. So if we plug it 25 instead of U, so it will be easy to find it out. The V values, V value is coming here around 986 liter. So we found out what is the volume of Plugflow reactor will be required for this kind of reaction. So most of the equation till now whatever is solved, essentially very similar and simplistic approach. Let's see another example here. This is something different, of course. It is a gaseous feed of pure compound A. Here concentration is given 2 mole per liter and 100 mole per minute. So this is Fa, and this is mole per liter is concentration Ca. So Ca Fa. So I know the volumetric flow rate also, which decomposes to give a variety of products in a Plugflow reactor. So you try to understand. The kinetic of the conversion is represented by a simplistic approach. A equal to 2.5 P. Here it is something different one. We need to understand. We will focus. And Ra is given. Ra equal to 10 into Ca. Okay, very nice. So in this case, what is going to happen here? Actually, the product formation is going to increase the volume. So essentially the simplistic approach, we are assuming that the volume remain constant, is not true in this case. So we need to find eta here. Let's see how you are doing this case. And we are asking find the expected conversion in a 22 liter reactor. So reactor volume is given. In this case, what will be the conversion? Now anyway, our equation will remain unchanged, and we need to calculate eta equal to, so when it is 100% converted, it is 2.5 p will be the volume. 2.5 starting is 1, so a initially a, all a is being converted means it will become 2.5. so 2.5 minus 1 by 1, so essentially it is becoming 1.5 is the value for eta. Keep it there. Now coming into our expression, or we'll say performance equations for Plugflow, same. Actually we are repeatedly doing the same job. So instead of minus RA, we can write 10 CA. We are plugging it. CA we have to convert into in terms of XA. So earlier we were writing CA was CA0 into 1 minus XA, that was original one, but you see now eta is coming over in this picture. So as eta is coming over, we have already shown you earlier that CA and XA, how is it related when eta is there or where volume is changing. So it is becoming 1 minus XA 1 plus eta XA, that's all. Otherwise the expression is no change. So we are plugging it back. Eta value is 1.5, we already know. So if we put it back, 1 plus 1.5 XA, 1 minus XA, and CA0, see this CA0 and this CA0 is actually cancelling out each other. This 10 is becoming, when it is coming out, and just writing 0.1. So this thing you can actually solve. This integration is possible to solve. We are assuming initial XA equal to 0 and final is XA only. So in terms of XA we can write out. So tau is, for example, tau means volume. So volume is 22 liter, and flow rate is easy to understand. You see, flow rate is actually 100 mole per minute, and 2 mole is there in 1 liter. So for 100 moles we need actually 50 liter, so it is 100 by 2, 50 liter per minute. So this is flow rate. So 22 divided by 100 by 2. This calculation I hope you understand. This is volume, this is total volume, and this is flow rate rather. So 100 by 2. So plugging it back, remaining is only XA, so probably you can solve. So this integration we are doing minus 1.5 XA minus 2.5 ln 1 minus XA equal to 4.4. Now this case solution is not so straightforward. We can do in mathematical solver, but for pen and paper solving we need to have some simplification, because ln 1 minus XA and XA, they are not really solvable using your calculator. So in this case, if it is not like that, then ln 1 minus XA can have expression which is simplified also. We will discuss it later on, not exactly in this case, but it can be solved if you know. Now the third example we are going to take, it is something similar and somehow different also. Now earlier we were discussing all about Plugflow, and this time we are going to have a mixed flow reactor. But you see this problem is very similar to the earlier one. Aqueous feed stream 25 liter per minute, so flow rate is given, 95% conversion we are expecting, CA0 is given, kinetics also given, it is enzyme kinetics, and we can show you similar expression, exactly similar expression. Now what will happen in this case, what volume we need. So we are looking for how much is the volume of the mixed flow reactor. So mixed flow reactor expression is similar, but integration is not there. So tau actually we can write equal to CA0 into XA by minus RA. Very straightforward, because now XA we already have done. In terms of RA, in terms of XA we have already done. So RA equal to, in terms of CA we are going to change CA0 into 1 minus XA you are doing. So essentially whole block RA is simplified in terms of XA. So once you derived or we have converted RA in terms of XA, we can put it back. So essentially tau is becoming CA0 is 2, and this is we already know 0 0.2 into 1 minus xa 2 minus x. If we plug it back in our expression, so you can see uh, the tau is coming in terms of xa, whole block coming from original xa. This xa was already there, and ra we have substituted, so it is becoming I'm just leaving it here. You can do the calculation again, and xa we need to know 95% conversion. So xa we know 95%, so 0.95 I'm plugging it here, you see. So once we plugging it back, this value is coming 199.5. so tau is becoming 199.5. Tau equal to V by flow rate. So flow rate is given 25 liter per minute. So flow rate is volumetric flow rate is known, and this is the reactor volume. So V is coming around 4987 liter. So essentially from these three problems we understood how can you deal most of the problems can be solved in a simple way. We need to understand the general expression for mixed flow, plug flow, reactor system, or even in batch reactor system they are very similar to one another. Only thing is that the rate expression for RA is the more important parameter, where most of the time the expression is given in terms of concentration. You need to convert them in terms of XA, fractional conversion, or the opposite one. If it is dxa, you need to convert it in terms of concentration and do the integration. So it is actually inhomogeneous. One is concentration, one is x. You need to make it homogeneous and do the integration part if possible. And if it is done, the rest of the problem is really very simple to solve. We'll come over for new example in coming class.